Uh, okay, so our first speaker, our first guest speaker for 2025 is Faidon Andriopoulos, who is going to talk about the motivic filtration of TR, p-adic phenomena in cohomology theories.
Okay, great. Thank you very, very much for the kind invitation. Let me also take the chance to wish everyone a happy new year. So, um, my title is going to be about certain p-adic phenomena and how they show up in cohomology theories. Essentially, the goal of my talk is to try to um, discuss the keywords that show up in the title. There will be essentially two parts. One will be certain motivational aspects, but there will also be some concrete calculations. So whatever happens, if you feel you don't understand something, especially at certain points where I'm a bit vague, please feel free to stop me, and I'll try my best to explain what's going on. Okay. Oops. Okay. So there will be three parts. We'll start with some motivation from topology, then we will go into some p-adic calculations, and then for the last part, I will try to explain the keywords of the title. Okay, so for the first part, what is a cohomology theory? Uh, so cohomology theories naturally show up in the realm of topology. Um, Given a nice space, X, say a smooth manifold or a ZW complex, cohomology theory serves as a linearization of its data. Essentially, what we have is the following. We start with a space. Taking its cohomology theory should give back, say, an abelian group or a vector space or a module, something that remembers some of the data of the original space, but linearizes so that we can handle it in a much easier way. There are many different ways of producing a cohomology theory. And the question is, how do we compare them to each other? For example, say that we have a smooth manifold X. In topology, there is quite some flexibility to move around topological cycles. This is something that allows us to compare objects of topological nature with objects of analytic nature. So what is a very standard example that one studies in a, say, first class on manifolds? That is the period isomorphism. The period isomorphism is something that compares objects of completely different natures. On the left-hand side, we have Durham cohomology, which is something of analytic nature, essentially differential forms. And on the right-hand side, we have singular cohomology, which is something that tries to understand topological cycles of the manifold. The two are compared to each other, essentially. They're isomorphic to each other after tensoring here with C. By doing what? Well, we have a differential form, and we integrate it over the topological cycle. The key tool in this in building this isomorphism is the Poincare lemma, which tells us that, say, higher Durham cohomology groups vanish in like local places of the local open subsets of the manifold. So that is a very concrete way or somewhat concrete, but it is a very concrete theorem, say, on how two cohomology theories compare to one another. Another question would be, what happens when we deal with, say, more complicated theories? Such a more complicated theory is complex topological K-theory, which instead of looking at, say, cycles or differential forms on a manifold, what studies is the category of its vector bundles. So what is topological K-theory? How do we build it? Well, we start with vector bundles and look at their isomorphism classes. When we have two vector bundles, essentially locally, what these are is just, say, like a trivialization of vector bundle just gives us a vector space on a manifold. So what we can do is we can add them together by taking direct sums. When we look at the isomorphism classes, they form a monoid under the operation of taking direct sums. So formally, we can add two isomorphism classes by taking as a result the isomorphism class, which corresponds to the direct sum of the two vector bundles. This is a monoid. Out of this monoid, one can construct an abelian group by the procedure called the group completion, or say the Grothendieck group. What is the Grothendieck group of a monoid? It is the simplest way of extracting an abelian group out of that monoid by, say, formally adding inverses. So what one does in this particular situation is, well, we have the direct sum. Formally adding inverses should also produce an inverse to the addition, which is the direct sum. So this is just, excuse me. This is just an abelian group. When we apply this procedure to the category of vector bundles with this addition that I just described, gives us the K-theory of the space. This should be thought of as the zeroth cohomology group. There is a trick one can do in topology and create higher groups by modifying the space. So if this is thought as K0, then one can build all the other K-theory groups by applying the same construction at modifications of that space, which is a procedure called taking suspensions. If you know what it is fine. It does not really matter. All that I'm trying to say, all that we can take out of that is that K-theory can be constructed on the space, and then by taking some modification of the original space, one can have a complete cohomology theory and not just K0. This is a very formal, all these are very formal constructions. The question is, how can one try to understand what, say, this topological K-theory is? The trick is to break it down into simpler pieces by first breaking down the original space. What could one do? Well, we're still in topology, so that means we have quite some flexibility. What we can do is we have our original space, and we can filter it using the skeletal filtration of the space. So for example, assume that X is, say, a CW complex, then we can filter that complex by allowing cells of an original dimension. This produces a filtration on the K-theory itself, which allows us to compute it in terms of some simpler cohomology theory, for example, singular cohomology. In particular, one has a spectral sequence called the Atiyah-Hirschsprung spectral sequence, which tells us that, well, we have K-theory equipped with this filtration that we get by filtering the original space. The graded pieces for that filtration can be computed in simple terms by the singular cohomology. So what is the takeaway, like, even vaguely, from these two phenomena? One can understand relations between cohomology theories by either trying to produce a direct link between them. So say you have two cohomology theories, you can try to hook up a map from one to the other and prove that it is an isomorphism, as for example you do in the period isomorphism that I described previously. Or if you have a general cohomology theory, as for example topological K-theory, which has nice properties, but it is very formal and difficult to capture, what you can do is break it into simpler pieces and try to understand them by using simpler cohomology theories like singular cohomology. Okay, I know that this might be a bit vague, but I want to have these two different techniques serve as an example of what is going to come. Okay, so let's slowly try to go into the p-adic world. What we would like to do for the remainder of this talk is try to bring this set of ideas, the two different versions that I briefly described, in the realm of, say, algebraic geometry. So algebraic geometry is at least its modern incarnation, is a pretty recent subject, which was its foundations were mainly laid out by Grothendieck and his peers and his students. And well, as in topology, one of the main tools that they used in order to tackle the problem that arose in this field were to construct different cohomology theories. So I have some examples here. If you don't know them, it is fine. Singular cohomology, Durham cohomology, et al., so on and so forth. The question is, how do these cohomology theories compare to one another? The problem is, originally, cohomology theories were defined in the realm of topology, where one has a lot of space, as I already said, for example, in the case of constructing the period isomorphism. And this allows for a lot of flexibility. However, the problem in algebraic geometry is that it is a very rigid subject. So it is very difficult to get comparisons between different cohomology theories. This led to a very large vision by Grothendieck and his school, which came under the name of motives. The general idea is that there should be a single way to extract linear data out of a space, say a scheme over a variety, and that single way should be called motivic cohomology. And then, given the different natures of the constructions of all the other cohomology theories, there should be a specialization from that, say, if you wish, motivic cohomology to the other ones. Funnily enough, I didn't know this when I started reading things, but it's really interesting, the fact that the original name for motive comes from painting. The idea came from Cézanne, an impressionist painter, who I don't know if anyone has ever looked at. Maybe you have looked at one of his paintings. The idea is that there are different ways to depict a scenery, given, say, the changes in weather or in light. But the belief is there is a unique object in which a painter studies. In analogy, why, like the reason Grothendieck probably chose this name is that there are various incarnations of cohomology theories, but there should be some true one which sort of encodes all the data that one wants. Okay, so in the realm of algebraic geometry, we usually want would usually like to study a scheme or a variety over the rational numbers, or say over the integers. To begin with, that can be a quite difficult problem. So usually one has a key principle from number theory, which is the following. Instead of trying to study that scheme over Q or over Z, instead, what one can do is try to first tackle a modified problem and try working over a single prime. What this means is, instead of working over the rationals or over the integers, one should usually work over the p-adic rationals or the p-adic integers, and then try to, like, when the problem is done, try to glue things back together in order to obtain a global result over Q or over Z. So let's start with a reminder. What are the p-adic integers? So for whatever we do, and for the rest of this talk, P is a fixed prime number. The p-adic integers can be constructed as follows. You start with the integers Z, and you mod out with a power of the element P to the n. If we look at different powers of n, this gives us a tower, like here. Taking the limit of that tower gives us back the p-adic integers. And furthermore, if we invert P, we get back QP, which is the p-adic rational numbers. This is a pretty algebraic construction. If one wants to think of it in terms of, say, topology, we can think of the p-adic rational numbers as the topological completion of Q with respect to the p-adic absolute value, which tells us the degree of, say, divisibility by P of a given rational number. Okay. The description of which I gave a reminder is a quite concrete one. However, there is a more elegant description of the p-adic integers, which can be obtained by the use of the Witt vectors. So what are the Witt vectors? This is a very, say, important and also simple mechanism that one uses in this field. So given a ring A, one can construct a new ring WRA called the ring of R-truncated Witt vectors. This is a ring, essentially this is a tower of rings for R an integer between 1 and infinity. So for every integer, given a ring A, we construct a new ring WR of A. So how does this look? As I said, it is isomorphic to a product of R copies of A of R. But the ring structure of WRA, so in particular the addition and the multiplication, behaves very differently than, say, the ring structure that one obtains on A to the R as a product ring. In particular, it encodes polynomials and power series in the variable P, which is the fixed prime number that we have. In particular, WR of A is defined as follows. There are so-called ghost maps for every integer R, which are ring homomorphisms. So WR of A is defined as the unique ring which comes with a ring homomorphism to A of R, given as follows. There is WR of A is given by an R tuple of elements in A, and it sends to an R tuple of elements in A of R, subject to the following conditions. So W0 should be the same as A of 0, and then the rest of Wi, we should think of them as, say, polynomials, or when we take the limit, power series in the variable p. The Witt vectors have a very rich structure. Some of the most important is the following. We have a restriction map. So we're talking about like R tuples of elements. So there is a natural restriction map which takes us from WR plus 1 of A to WR of A, and takes an array of R plus 1 elements to an array of R elements by just forgetting the rightmost entry. We have the so-called Witt vector Frobenius, which again takes us from WR plus 1 of A to WR of A. But this time, this is an application on the right-hand side of the ghost maps, takes a R plus 1 tuple of elements to an R tuple of elements by forgetting the leftmost entry instead of the rightmost one. And there is also the so-called Versenburg map, which takes us to the opposite direction from WR of A to WR plus 1 of A, and takes an array of R elements to an array of R plus 1 elements by just inserting the 0 on the leftmost entry. The most important, all these operations on the vectors are F and V. They have several relations that they satisfy, but the most important one is the fact that F, after first applying V and then applying F, gives us back P. In general, taking the limit with respect to these restriction maps gives us back the Witt vectors, which we just write as W of A, which again, as a set, is isomorphic to an infinite array of elements of A, but the ring structure, the addition and the multiplication, encode a power series in the variable P with coefficients in A. So one can go back to the previous identification of ZP and have a new one via the Witt vectors. Namely, there's this magic mechanism of the Witt vectors to which if we insert FP, we get back the p-adic integers. One way to think about it is as follows. What are the p-adic integers? They're just power series in P with coefficients in FP. This is exactly what this identification tells us. Namely, Witt vectors are power series, and the entries in the coefficients are FP. In particular, the way to construct the isomorphism between the two different descriptions is observe that when we have the integers z mod p to the r, this is the same as the R-truncated Witt vectors. So one can start from the case of r is equal to 1, where we have trivially that z mod p is the same as fp, the field with p elements, and then go up the tower by constructing maps from wr of fp to z mod p to the r. Taking the limit gives us back that the p-adic integers is the same as the Witt vectors of fp. An equivalent way to think about this identification is that we have a projection map from ZP, which is identified with the Witt vectors of fp, to the R-truncated Witt vectors of Fp, which we already said is equivalent to Z mod P to the R. The kernel of this projection map is just generated by P to the R. By the way, note that it does not matter whether we use Frobenius or restriction in the case of Fp when we take the inverse limit. This has to do with the fact that Fp is a perfect ring, so whether we take the inverse limit with respect to R or with respect to F should always give back Zp. Okay, so this construction of the Witt vectors and the identification of the Witt vectors of Fp with the p-adic integers is the most important building block for what is to come. Are there any questions so far? Okay. So what happens if the input, the Witt vector mechanism, is not of positive characteristic, but of mixed characteristic? So far what we did is we took Witt vectors of a ring that is of positive characteristic. What if we try to insert something larger? Remember, Witt vectors make sense for any ring. So a construction that is used is frequently done in number theory is to start with QP and try to build something larger. Usually when we have Q, not the p-adic completion, but just the standard rational numbers, we complete them with the usual absolute value to obtain the real numbers, and then, sorry, this is topological completion, and then take algebraic completion to get back the complex numbers. One can do a similar procedure, but instead of using the absolute value, which the standard absolute value, one can use the p-adic absolute value. So what we can do is start with QP and take QP bar, which is the algebraic closure of the p-adic rational numbers. Then we can take hat, which is the topological completion with respect to the p-adic absolute value. And this gives us the p-adic version of the complex numbers. It is sort of done in a completely analogous way to how we extract the usual complex numbers out of Q. The only difference is we're essentially using the p-adic absolute value. Together with the p-adic complex numbers comes OC, which is its ring of integers. So C is obtained by OC by inverting P in analogy to how we obtain QP as ZP by inverting P. By the way, if these rings, if this means anything to anyone, this is a standard example of a perfectoid ring. So in particular, FP is a perfect ring in the setting of characteristic P. OC shares some similarities, but in the realm of algebra in mixed characteristic, not positive characteristic. So one could try to do something similar as to what we did in the previous slide, but instead of using FP, we can try to use OC. Okay. There is a standard construction of Fontaine which does the following. So what we did previously is we took the R-truncated Witt vectors of Fp, and we took an inverse limit, say with respect to Frobenius, to get back Zp. Fontaine did a similar construction. Instead of having Fp here, the input was that of OC. So you take R-truncated Witt vectors of that ring, which is already pretty large, and take the inverse limit with respect to the Witt vector Frobenius maps. This is Fontaine's A ring. And since we're taking inverse limit with respect to the Witt vector Frobenius F, it comes equipped with a Frobenius automorphism with a Greek we denote with a Greek letter phi. So we took the truncated Witt vectors of a very large ring, and we took inverse limit with respect to Witt vector Frobenius. So this means since we took an inverse limit, we have standard projection maps from the limit to the initial members themselves. This is something that happens for every R. So we denote these projection maps by theta r tilde going from A inf to the R-truncated Witt vectors of OC. The question is, what can we say about the kernel of these projection maps? Note that, let me go back to the previous slide. Before, when we had these projection maps from ZP to WR of FP, the kernel was generated by a power of P. So the question is, what happens in this more, say, complicated case where when the input is not a finite ring, but something much larger? So one of the very famous constructions of Jean-Marc Fontaine, which serves as a foundation of p-adic theory, is that the kernel of the map theta tilde 1 is generated by a single element, which we denote by xi tilde. I'm not going to give a concrete construction of how one proves that the kernel is generated by a single element, but I would like to think of it as a generalization of the previous situation where we had FP instead of OC. The general situation is that we have these projection maps from theta r tilde, and they're generated for every R by a single element. In the case R equals 1, where we take the map from A to OC, they're generated by a single element xi tilde. In the case of higher integers R, the kernel generated by a product of xi tilde with xi tilde together with applications of the Frobenius that we have on A. So it's just this product of xi tilde with 5 xi tilde, etc. But in any case, all these projection maps are generated by a single element. In a similar fashion, instead of theta r tilde, one can also have untwisted versions of these maps, where we precompose with a Frobenius on A inf and obtain maps theta r from A inf to WROC. Their kernel is generated instead of by the elements xi r tilde, they're generated by elements, I call them xi r, which are inverse images with respect to the rth power of Frobenius of this xi r tilde element. So what we have for this large class of, for this particular very large ring, is an analogous description as before. So we obtain, we can obtain the Witt vectors of a very large ring by taking quotient with respect to a single element. So before we had ZP mod P to the R give us back WR of FP. Here we have A inf mod xi R give us back WR OC. It doesn't matter whether we input out by xi R or xi R tilde. One is a Frobenius twist of the other. Okay, so the takeaway from this from Fontaine's theorem is that this pair of A, this very large ring A, together with xi tilde, behaves similarly to the pair of ZP with P. So what one does in p-adic Hodge theory, excuse me, what one does to in the setting of p-adic Hodge theory is try to build very large rings called period rings in an attempt to reincarnate the period isomorphism that we had in topology, but in the case of, say, working with a scheme or a variety over QP. So these very large rings, for example, look as follows. We have A, we can invert P, and then we still have this element Xi living in A. We can take completion with respect to powers of Xi. This gives us the even larger ring BDR plus with fraction field BDR. The DR here stands for Dirac. These very large rings allows for a p-adic version, as I said, of the period isomorphism, which was, I mean, it came as a set of conjectures originally by Fontaine, and then it has been proven by a set of different people using actually very, very different techniques. For example, Faltings uses some elements of his, actually several elements of p-adic Hodge theory. Niziol uses algebraic K-theory, and there is also the proof of Belenson, which is quite original in style to the, sorry, it is quite similar in style to the original period isomorphism that is seen in topology. The main ingredient is a p-adic version of the Poincaré. So what does the period isomorphism look like in, say, in this setup? We can assume that X is a smooth variety over QP. Then we have an isomorphism where instead of analytic theorem and singular cohomology, we have cohomology theories in the realm of algebraic geometry. So on the left, we have an algebraic version of the realm cohomology. Originally, the realm cohomology is something analytic in style, but one can define a completely algebraic version of the realm cohomology by having a formal version of differentials on the level of modules. And on the right-hand side, instead of singular cohomology, one has the so-called étale cohomology, which in the case of algebraic geometry, it sees very well local aspects of the space. When we have them as they are, so the realm cohomology of X and étale cohomology of X with QP coefficients, they're not really related to each other. But once we base change to p-realm coefficients, this gives us this p-adic version of the period isomorphism, which in particular comes with a very rich structure. For example, one has a Galois action on both sides, which is respected by the isomorphism. There's also a filtration on both sides. On the left-hand side, it comes from the Hodge filtration and cohomology, and on the right-hand side, it comes from the filtration of BTR with respect to its uniformism. Okay. I'm not going that. I'm going to move on to more concrete calculation, but I just want to give a feel of how this construction produce, say, analogous results in the realm of algebraic geometry as in the realm of topology and theory. Okay. Are there any questions or comments so far?
Sorry,
Yeah.
can I ask something really quick?
Mhm. Yes, yes, of course,
It's
please.
just about the Frobenius definition that you gave on Witt vectors. I'm more used to the definition that, you know, takes its coefficient to its pth power, let's say, and not the one you gave. Where can I find the one you defined? Because I haven't seen much about Witt vectors, but even in Jacobson or Rabinov's notes or whatever I've studied, they don't give this particular definition of the Frobenius on Witt vectors. Where can I find it?
Okay, so
Yeah,
that's a great question. So here's the thing about Witt vectors and the sources one can study.
yeah.
Usually in number theory, what people do is say they only take Witt vectors of things that live in characteristic P. So the usual Frobenius that one has in characteristic P is the endomorphism that you said that takes an element to its pth power.
Mm-hmm.
And then say once you apply Witt vectors, you get a lift of that endomorphism to Witt vectors, like to an endomorphism of the Witt vectors. However, um, this like usual Frobenius that you mentioned is something different from the Witt vector Frobenius, and they're only identified when the input in the theory of Witt vectors. Where is it?
Mm-hmm. Mm-hmm.
When the input is of characteristic P.
Okay.
In general, they're quite different, or I can share, like after I'm done with the talk, I can definitely give you some sources where you can see things, how you can see how things go with the general theory of Witt vectors. Okay,
Okay.
I'd be very happy to do that.
Okay, thanks a lot.
Yeah, of course. Yeah, but what you said is it's something very very important. Actually, has to do with this identity. And it only happens when the input, say, is of characteristic P or something similar. Okay. Okay. So I want to move to by the way, I'm not exactly sure how I'm doing with time, but I'll try to be quick. So I want to move to the last part, which is try to use like so far we've done the following. We started with some motivation from topology, and we asked ourselves, say, how could different cohomology theories relate to each other? As we said, one direction would be to try and build concrete connections between the two, as in the period isomorphism or its p-adic incarnation in the realm of algebraic geometry. The other is try to start with something formal, which has nice formal properties, and try to break it down into simpler pieces. So this is what we're going to do from now on, try to use simple calculations in order to try to understand formal aspects, or say formal constructions in cohomology theories. Okay, so as I said, as in the case of topology, one can take a different route. We can start with an invariant, say K theory, which has good formal properties, but it's somewhat difficult to capture, and try to break it down into simpler pieces in order to try and understand, say, get a better feel of the theory. There is a question. So why when we take, so the question is the following in the chat. Why when we have the p-adic integers mod p to the r, this is the same as the integers mod p to the r. So the idea is, so what are p-adic integers? They're power series in p. The way to think of modding out with p to the r is we only allow terms up to order r. Okay, so if you have a power series, it should be something as follows. So you have A0 plus A1 times P plus A2 times P to the power of 2 plus dot dot dot. Okay, so when you mod out by P to the R, you only allow terms like essentially polynomials in P up to the degree of R minus 1. And this by definition is Z mod P to the R. I'm pretty sure you can also get a reality check of why this happens by just looking at by counting elements. Z mod P to the R is a finite ring, so you can probably get a feel of the fact that Z mod P to mod out by P to the R is the same by essentially guessing that they have the same number of elements. I don't know if this makes any sense. Okay, so back to K theory. Oops. So I gave a pretty quick definition of topological K theory. What is its algebraic version? One can start by doing the exact same procedure. So in topology, we have the category of vector bundles of the particular space. Here, instead of vector bundles, we use projective A modules. They have we can still take, they're A modules. We can take their direct sum by applying the group completion construction out of the monoid of the projective A modules together with the direct sum. We get back an abelian group. That is K0 of A, or equivalently, it's also called the Grothendieck group of A. Constructing higher K groups is something definitely not trivial. The original definition goes back to Quillen, for which he got the, for that work, but also, that was the main work for which he got the Fields Medal. Of course, there are several years since that time. This happened in the 70s. People have reworked the original definition. And well, if one studies, say, the theory of infinity categories, there's a higher categorical version of the original group completion that gives the answer. In particular, there's a spectrum, if you know the name in the term of homotopy theory, or you can just think of it as a space, which once we take its homotopy groups, we get back all the higher K theory groups. In particular, pi 0 of that space, K of A, should give back the Grothendieck group. Okay, so as in topology, this is where the motivation comes from. The general motivation tells us the following, as in the topological K theory case, that the algebraic K theory should be equipped with a certain filtration. In topology, this comes from the skeletal filtration, but here we don't have that much flexibility. And its graded terms, they should be computed in terms of this, say, motivic cohomology that I mentioned before, which should specialize to all the other cohomology theories. Okay, so we have this pretty complicated K theory, which is a generalized cohomology theory, and there should be a way to break it down to simpler pieces by studying a filtration on it. This has been done in nice cases, but it's still difficult to capture. So let's try to break the problem down even more. So instead of talking about K theory, let us try to talk about a relative version of it. So what is relative K theory? Given a ring and an ideal of that ring, we can define K theory of A, I as the fiber of the map of K theory of A to K theory of A modi. This is just the map induced by taking A to the projection to A modi and then applying K theory. So in this particular case that we're interested in, we're going to take a very specific situation. So we're going to start with a ring A and then look at the relative K theory of A of t mod t to the n, so truncated polynomials relative to the ideal t. Okay, we can take that. We can start with that relative K theory, and then take the inverse limit with respect to n. Here, the pre-completions that I've taken is that so that I don't have to care about various prime numbers. I just want to have results about a specific prime p, but I can have these. There is a version of this equivalence that I'm going to discuss in the non-complete case. So I have relative K theory, and I take its inverse limit. There is a series of results in these curves in K theory business, which is this particular case of relative K theory, which tells us that this gives this object on the left-hand side, which is called TR of A, which is of quite different nature compared to K theory. One way to think of it is in terms of this comparison between two different types of data that we've already discussed. We usually think of K theory as carrying topological situation. The left-hand side does not carry topological situation; it carries de Rham situation. So this equivalence, whatever this TR is that I have not studied yet, is something that compares differential forms on the, say, left-hand side with topological data on the right-hand side. So what is this TR? It is something that looks like the Witt vectors. So first of all, it comes as a limit of a certain tower of rings in the, say, sense of homotopy theory. So as also happens in the case of Witt vectors, TR is the inverse limit of a tower of R truncated objects. Starting from the case of R equals 1, which is topological Hochschild homology of A, if anyone knows those, for anyone that knows those keywords, there's one can build up a tower whose inverse limit gives this weird complicated object that is TR. So let's look, instead of looking at the entire limit, let's take one of these truncated pieces. So what is this truncated version of TR to the R for, say, a finite number R? These are spectra in the sense of homotopy theory, just as in K theory. So this is something that comes with, if you wish, you can think of it as a space. So it has homotopy groups. But in this particular case, it is connected. So it does not have negative homotopy groups. The negative homotopy groups vanish. It has an S1 action, which is really critical in what I try to say, that it is of de Rham nature. For those that have looked at the theory of Hochschild homology, this is considered as a non-commutative version of the de Rham differential. And just as in the case of the Witt vectors, one has restriction, Frobenius, inversible operators, as well as ghost maps. So one way to think of, of TR is as a, say, a higher version of the Witt vectors. In particular, from this theory, which is which lives in the realm of homotopy theory, one can get back the Witt vectors over ring A by just taking the pi 0 of the R truncated TR. This is a very important result by Hesselhoff and Matza. In particular, this equivalence respects the restriction Frobenius and Versibel on both sides, where on the right-hand side, they're defined algebraically. On the left-hand side, they come from, actually, they're related to the echelon action on TR. So what this means is that we can think of these invariants as follows. So TR is essentially Witt vectors, which sit in degree 0 on the 0th homotopy group of TR, plus some higher data, okay? So to recap, what we've done is we started from K-theory, which is something that, say, looks at vector bundles of a variety, and by taking inverse limit of truncated polynomials, we get back TR, which magically, if you wish, gives rise to the Witt vectors again, but say from a categorical viewpoint. So let's get into some computations to get a feel of what's going on. By the way, are there any questions before I get into the computations? Okay, I'm not exactly sure how I'm doing with time because I don't remember when I started, but I don't have a lot of material to go through yet. If I'm going over time, please let me know. So let's check what happens for the case of input of instead of having a general ring A, having the input of FP, field of P elements. So there's a very, very important and deep theorem due to Beckstead, which tells us that the case of R equals 1, which is the case of topological Hochschild homology, everything is concentrated on even degrees. So when we look at homotopy groups of, say, TR1 or THH, it's the same, different names for the same object, of FP, all negative homotopy groups vanish, and all odd homotopy groups vanish as well. The ones that remain are the even ones, and we have the structure of a polynomial ring. So when we look at pi star of THH of FP, we get back polynomials, the polynomial algebra over FP with a single generator sigma sitting on degree 2. Okay, this is a class from pi 2 of THH of FP. So this is the case of R equals 1 in this tower of R truncated TR. What happens when we look at higher R's? So there's a similar picture. Instead of FP, what one obtains is the R truncated Witt vectors of FP. There is an interesting back and forth between the S1 invariants of the R truncated TR and the original TR. This we think as, say, the Ramp as an analog of the Ramp cohomology groups. This we think as an analog of, say, the original Durham complex. So when we look at the even homotopy groups of after passing to the invariants for the echelon action that TR carries, we get back the filtration on ZP by powers of P. Going back to the original TR, instead of the filtration by powers of by powers of P on ZP, we get back the associated great pieces, which are identified with the truncated Witt vectors of FP. In terms of polynomial algebras, we have a similar description. So as the original computation of Beckstead, instead of in the original computation of Beckstead, we had FP on sigma. Here, the polynomial algebra on TR of R gives us back the R truncated Witt vectors of FP as a polynomial algebra on a single generator which stands in degree 2. One can also rewrite what happens in the case of the S1 invariance of TR, where we have the negative homotopy groups of this object do not vanish. So we have a polynomial ring in 2 generators. U stands in degree 2, V stands in degree -2. And the relation that they have together is that when we multiply them, they give us back p to the r. Okay, and it turns out that this object carries a motivic filtration, which comes from the double speed tau, the double speed Whitehead tau. So this means we have exact computation on what happens with the homotopy groups. The orthomotopy groups vanish, so we only need to take into account the information that comes from the even homotopy groups. And when we look back at the associated graded pieces, the associated graded terms for this filtration, which is just the Whitehead filtration, should just be the computations for the even homotopy groups of the invariants. One can go on and, from the case of FP, move upwards to the case of OC by essentially exploiting the similarities between, instead of having the pair of ZP with the element P, using the fact that A with the element psi tilde that we discussed previously, which is obtained from Witt vectors of OC, that they behave in very similar terms. So there is a very similar computation that one can do. In particular, when we look at TR of OC, passing to its S1 homotopy fixed points, instead of the filtration with respect to powers of P that we had in the previous situation, here we have a filtration by powers of psi r. And going back to the original TR, its even homotopy groups can be described in terms of the associated grade terms of that filtration. So here we have a filtration, and here we have its graded pieces, which can be identified with the R-truncated Witt vectors of OC. In terms of polynomial rings, on the left, we have a similar version as to the one that we had for FP. The only difference is instead of WR of FP, we have WR of OC, which is a polynomial ring in a single generator. And the description for the object on the right-hand side, essentially we replace P to the R here by psi R and ZP by A. Again, in a very similar fashion. Excuse me. The motivic filtration on TR is obtained by a concrete calculation. It comes from the double speed Whitehead tower as in the previous situation. Sorry, this shouldn't have been FP. This should have been OC. But both the cases of positive and mixed characteristic are the same. In all these invariants, the autohomotopy groups vanish, and the motivic filtration essentially comes by just looking at what happens on the even degrees. Okay. And now, for the final slide, there is the question of what one can say for the general case of instead of having FP or OC, what can we say about the input of A, which say, some nice p-complete ring, for example, some smooth ring. This is the original case, going beyond the simple calculations that is studied in the second article of Batmorov and Solze, whose techniques we use. In particular, what they studied is the case of R equals 1, the case of topological Hochschild homology, by using their techniques, which is first doing these calculations that we did, and then moving further by extending those calculations to even larger class of rings, and then using some version of descent theory. There is a possibility of extending the motivic filtration from the cases of FP and OC, or say other perfect or perfectoid rings, to a larger class of rings, and actually identify their graded pieces, which is what we wanted to do in the original case. More specifically, there is a topology called quasi-symptomic topology, locally for which one can identify the graded terms of these motivic filtrations. The one that is associated to the S1 homotopy fixed points of TR should be identified again locally for that topology as a filtration on some prismatic cohomology groups. Going back to the original TR from its S1 homotopy fixed points, the identification that we get is that of going from this filtration to its associated graded pieces. In particular, one can go back to the original Witt vectors by taking the zeroth associated graded term for that filtration, which essentially one can think of as a, say, different definition of the vectors. So maybe I will stop here. I'm not sure if I went over time, but thank you for your attention. I'm open for any comments or questions and discussion in general. Thank you.